In this video, we'll be examining the architecture of the convolutional neural network model. As previously mentioned, CNN is a type of neural network empowered with some specific hidden layers, including the convolutional layer, the pooling layer, and the fully connected layer. Let's start with the first layer, the convolutional layer. The main purpose of the convolutional layer is to detect different patterns or features from an input image, for example, its edges. Assume that you have an image and you want to find the edges from the photo so that you can define a filter, which is also called a kernel. Now, if you slide the filter over the image and apply the dot product of the filter to the image pixels, the result would be a new image with all the edges. That is, applying the filter to the left image will result in the right features that are typically useful for the initial layers of a CNN. In fact, the output is one of the very first primitive feature sets in the hierarchy of features. It is one of the key concepts behind CNNs. Now, the question is, what really happens mathematically when we apply a filter or kernel on an image? This brings us to the convolution process. Convolution is a function that can detect edges, orientations, and small patterns in an image. The convolution operation can be seen as a mathematical function. Imagine that we have a simple black and white image as you see here. We can convert the image to a matrix of pixels with binary values, where 1 means a white pixel and 0 represents a black pixel. Please keep in mind, however, that the most common usage is a value between 0 and 255 for a grayscale image, or a 3-channel image for a color image. But for now, and for the sake of simplicity, let's use 0 and 1 as our values. In this step, we define a filter. It can be any type of filter, even a random filter, but let's use the edge detector filter for now. Okay, now let's slide it over the image, and then calculate the convolved value for the first slide. Taking the values -1 and 1 on 2 adjacent pixels and 0 everywhere else for the filter results in the following image. Okay, now let's slide the kernel again. It will calculate the second element of our convolved image. We repeat this process to complete the convolved matrix. So, in essence, the convolution function is a simple matrix multiplication, and in this instance, the result shows us the edges of the image. Now, let's consider a handwritten digit that we want to recognize. We can apply a kernel to it. It is, in fact, the sum of element-wise multiplication of the kernel matrix and the image matrix, as shown on the previous slide. So, we can show the result as convolving a kernel on the image. Applying multiple kernels on one image will result in multiple convolved images. Now you can understand that leveraging different kernels allows us to find different patterns in an image, such as edges, curves, and so on. The output of the convolution process is called a feature map. At this point, you might be asking yourself, how do I choose or initialize the proper kernels? Well, typically you initialize the kernels with random values, and during the training phase, the values will be updated with optimum values in such a way that the digit is recognized. For example, here is the result of applying 8 different kernels on the digit 2. As you can see, each kernel will recognize a particular pattern in the digit. This is the first layer of convolutional deep learning. We can interpret this layer to traditional neural network terminology. The input image can be considered as a matrix that we feed into the neural network through input nodes. For example, in this case, the input layer of the network has 28 by 28 nodes. The output of the coevolution process are 8 of 28 by 28 neurons. we can assume those as hidden nodes. So, what are the weights between the input and hidden nodes? Yes, the 8 kernels, which are 5 by 5. Now we need to make a decision as to whether each hidden neuron should be fired or not. So we have to add activation functions to the neurons. We use ReLU, which is short for rectified linear unit, as the activation function on top of nodes in the convolution layer. ReLU is a nonlinear activation function, which is used to increase the nonlinear properties of the decision function. So, how can we apply it on a convolution layer? Well, we just go through all outputs of the convolution layer, convolved1, and wherever a negative number occurs, we swap it out for a 0. This is called the ReLU activation function. Now we have gone one step further. In this step, we have to downsample the output images from the ReLU function to reduce the dimensionality of the activate neurons. So, we use another layer, which is called max pooling. Max pooling is an operation that finds the maximum values and simplifies the inputs. In other words, it reduces the number of parameters within the model. In a sense, it turns the low-level data into higher-level information. For example, we can select a window of size of 2 by 2 and then select the maximum value for this matrix. That is, if the image is a 2 by 2 matrix, it would result in 1 output pixel. Also, in this step, we can define strides. A stride dictates the sliding behavior of the max pooling. For example, if we select stride equals 2, the window will move 2 pixels every time, thus not overlapping. Okay, now we should have our output matrices, but with lower dimensions. For example, 14 by 14. The next layer is the fully connected layer. Fully connected layers take the high-level filtered images from the previous layer, that is, all 8 matrices in our case, and convert them into a vector. First, each previous layer matrix will be converted to a one-dimensional vector. Then it will be fully connected to the next hidden layer, which usually has a low number of hidden units. We call it fully connected because each node from the previous layer is connected to all the nodes of this layer. It is connected through a weight matrix. We can use ReLU activation again here. And finally, we use softmax to find the class of each digit. Softmax is an activation function that is normally used in classification problems. It generates the probabilities for the output. For example, our model will not be 100% sure that one digit is the number 3. Instead, the answer will be a distribution of probabilities where, if the model is right, the 3 will be assigned the larger probability. That is, softmax can output a multi-class categorical probability distribution. Now, let's put all these layers together.